So it's my pleasure to introduce you to Geoff Hinton, who's a pioneer in machine learning, in neural nets, and more recently in deep architectures, and I think that's going to be the topic of today. So get over.
Okay, so I gave a talk here a couple of years ago, and the first 10 minutes or so will be an overview of what I said there, and then I'll talk about the new stuff. The new stuff consists of a better learning module, and I'll show you it learns better at all sorts of different things, like learning how images transform, learning how people walk, and learning object recognition. So the basic learning module consists of some variables that represent things like pixels, and these will be binary variables for now. Some variables that represent, these are latent variables, they're also going to be binary. And there's a bipartite connectivity, so these guys don't connect to each other. And that makes it very easy, if I give you the states of the visible variables, to infer the states of the hidden variables. They're all independent given the visible variables, because it's an undirected graph. And the inference procedure just says the probability of turning on hidden unit hj, given this visible vector v, is the logistic function of the total input it gets from the visible units. So very simple to infer the hidden variables. Given the hidden variables, we can also infer the visible variables very simply. And if we put some weights on the connections and we want to know what this model believes, we can just go backwards and forwards, inferring all the hidden variables in parallel, then all the visible ones. Do that for a long time, and then you'll see examples of the kinds of things it likes to believe. And the aim of learning is going to be to get it to like to believe the kinds of things that actually happen. So this thing is governed by an energy function. That is, given the weights on the connections, the energy of a visible plus a hidden vector is the sum over all connections of the weight if both the visible and hidden unit are active. So when a pixel and a feature detector are active, you add in the weight. And if it's a big positive weight, that's low energy, which is good. So it's a happy network. This has nice derivatives. If you differentiate with respect to the weights, you get this product of the visible and hidden activity. And so that derivative is going to show up a lot in the learning, because that derivative is how you change the energy of a combined configuration of visible and hidden units. The probability of a combined configuration, given the energy function, is e to the minus the energy of that combined configuration, normalized by the partition function. And if you want to know the probability of a particular visible vector, you have to sum over all the hidden vectors that might go with it, and that's the probability of a visible vector. If you want to change the weights to make this probability higher, you obviously need to lower the energies of combinations of a visible vector and a hidden vector that would like to go with it, and raise the energies of all other combinations. So you decrease the competition. The correct maximum likelihood learning rule, that is, if I want to change the weights so as to increase the log probability that this network would generate the vector v when I let it just sort of fantasize the things it likes to believe in, is a nice simple form. It's just the difference of two correlations. So even though it depends on all the other weights, it shows up as this difference of correlations. And what you do is you take your data, you activate the hidden units, they're stochastic binary units. You then reconstruct, activate, reconstruct, activate. So this is a Markov chain. You run it for a long time till you've forgotten where you started. And then you measure the correlation there, compare it with the correlation here. And what you're really doing is saying, by changing the weights in proportion to that, I'm lowering the energy of this visible vector with whatever hidden vector it chose. And by doing the opposite here, I'm raising the energy of things I fantasize. And so what I'm trying to do is believe in the data and not believe in what the model believes in. Eventually, this correlation will be the same as that one, in which case nothing will happen, because it'll believe in the data, or hopefully. It turns out you can get a much quicker learning algorithm, where you just go up and down and up again, and you take this difference of correlations. Justifying that is hard, but the main justification is it works. And it's quick. The reason these modules are interesting, the main reason they're interesting, is you can stack them up. That is, for complicated reasons I'm not going to go into, it works very well to train a module, then take the activities of the feature detectors, treat them as though they were data, and train another module on top of that. So the first module is trying to model what's going on in the pixels by using these feature detectors. And the feature detectors will tend to be highly correlated. The second model is trying to model the correlations among feature detectors. And you can guarantee that if you do that right, every time you go up a level, you get a better model of the data. Actually, you can guarantee that the first time you go up a level. For further levels, all you can guarantee is that there's a bound on how good your model of the data is. And every time you add another level, that bound improves, if you add it right. Having got this guarantee that something good is happening as we add more levels, we then violate all the conditions of the mathematics and just add more levels in a sort of ad hoc way, because we know good things are going to happen, and then we justify it by the fact that good things do happen. This allows us to learn many layers of feature detectors entirely unsupervised, just to model the structure in the data. Once we've done that, you can't get that accepted in a machine learning conference, because you have to do discrimination to be accepted in a machine learning conference. So once you've done that, you add some decision units to the top, and you learn the connections discriminatively between the top layer of features and the decision units. And then if you want, you can go back and fine-tune all of the connections using backpropagation. That overcomes the limit of backpropagation, which is there's not much information in a label, and it can only learn on labeled data. These things can learn on large amounts of unlabeled data. After they've learned, then you add these units at the top and backpropagate from a small amount of labeled data. And that's not designing the feature detectors anymore. As you probably know at Google, designing feature detectors is the art of things. And you'd like to design feature detectors based on what's in the data, not based on having to produce labeled data. So the idea of backpropagation was design your feature detectors so you're good at getting the right answer. The idea here is design your feature detectors to be good at modeling whatever's going on in the data. Once you've done that, just ever so slightly fine-tune them so you're better at getting the right answer. But don't try and use the answer to design feature detectors. And Yoshua Bengio's lab has done lots of work showing that this gives you better minima than just doing backpropagation. And what's more, minima in a completely different part of the space. So just to summarize this section, I think this is the most important slide in the talk, because it says what's wrong with nearly all machine learning, up till a few years ago. What people in machine learning would try and do is learn the mapping from an image to a label. And that would be a fine thing to do if you thought that images and labels arose in the following way. The stuff, and it gives rise to images, and then the images give rise to the labels, and given the image, the labels don't depend on the stuff. But you don't really believe that. You only believe that if the label is something like the parity of the pixels in the image. What you really believe is the stuff, it gives rise to images, and then the labels that go with images are because of the stuff, not because of the image. So there's a cow in a field, and you say cow. Now, if I just say cow to you, you don't know whether the cow is brown or black or upright or dead or far away. If I show you an image of the cow, you know all those things. So this is a very high bandwidth path. This is a very low bandwidth path. And the right way to associate labels with images is to first learn to invert this high bandwidth path. And we can clearly do that because vision works, basically. To first order, you look out there and you see things. And it's not like it might be a cow, it might be an elephant, it might be a lecture theatre. Basically, you get it right nearly all the time. And so we can invert that pathway. Having learned to do that, we can then learn what things are called. But you get the concept of a cow not from the name, but from seeing what's going on in the world. And that's what we're doing, and then later associating the label. Now, I need to do one slight modification to the basic module, which is I had binary units as the observables. Now we want to have linear units with Gaussian noise. So we just changed the energy function a bit. And the energy now says, I've got a kind of parabolic containment here. Each of these linear visible units has a bias, which is like its mean. And it would like to sit here. And moving away from that costs it in energy. A parabola is the negative log of a Gaussian. So it costs it. And then the input that comes from the hidden units, this is just Vi, Hj, Wij, but the V's have to be scaled by the standard deviation of the Gaussian there. If I differentiate that with respect to a visible activity, then what I get is Hj, Wij divided by the sigma I. And that's like an energy gradient. And what the visible unit does when you reconstruct is it tries to compromise between wanting to sit around here and wanting to satisfy this energy gradient. So it goes to the place where these two gradients are equal and opposite. And you have, that's the most likely value, and then you have Gaussian noise around there. So with that small modification, we can now deal with real valued data with binary latent variables. And we have an efficient learning algorithm that's an approximation to maximum likelihood. And so we can apply it to something. So there's a nice speech recognition task that's been well organized by the speech people, where there's an old database called Timit. It's got a very well-defined task for phone recognition, where what you have to do is you're given a short window of speech. You have to predict the distribution, the probability for the central frame of the various different phones. Actually, each phone is modeled by a three-state HMM that's sort of beginning, middle, and end. So you have to predict for each frame, is it the beginning, middle, or end of each of the possible phones? There's 183 of those things. If you give it a good distribution there, that sort of focuses on the right thing, then all the post-processing will give you back where the phoneme boundaries should be and what your phone error rate is. And that's all very standard. Some people use triphone models. We're using biphone models, which isn't quite as powerful. So now we can test how good we are at taking 11 frames of speech. It's 10 milliseconds per frame, but each frame's looking at like 25 milliseconds of speech, and predicting the phone of the middle frame. We use the standard speech representation, which is Mel-Kapstrel coefficients. There's 13 of those, and then they're differences and differences of differences. And we feed them into one of these deep nets. So here's your input, 11 frames of 39 coefficients. And then I was away when the student did this, and he actually believed what I said. So he thought adding lots and lots of hidden layers was a good idea. I'd have stopped at 2. But he added lots of hidden layers, all unsupervised. So all these green connections are learned without any use of the labels. He used a bottleneck there, so the number of red connections would be relatively small. These have to be learned using discriminative information. And now you back-propagate the correct answers through this whole net for about a day on a GPU board, or a month on a core. And it does very well. That is, the best phone error rate he got was 23%. But the important thing is, whatever configuration he used, however many hidden layers, as long as there were plenty, and whatever width, and whether he used this bottleneck or not, he gets between 23 and 24%. So it's very robust to the exact details of how many layers and how wide they are. And the best previous result on Timit for things that didn't use speaker adaptation was 24.4%, and that was averaging together lots of models. So this is good.
So each of these layers, that's 4 million weights?
Yep, 4 million weights. So we're only training 1, 2, 3, we're training, about 20 million weights. 20 million weights is about 2% of a cubic millimeter of cortex. Okay, so this is a tiny brain, but that's probably all you need for phoneme recognition.
So why did they start with the differences and double differences of the MFCCs if you're going into a thing that could learn to do that itself if it wanted to?
That's a very good question, and could you ask that again at the end? Okay. It's an extremely good question, because the reason they put the differences and double differences is so they can model the data with a diagonal covariance matrix, diagonal covariance model, and you can't model the fact that over time two things tend to be very much the same without modeling covariances, unless you actually put the differences into the data and you model the differences directly. So it allows you to use a model that can't cope with covariances. Later on, we're going to show you a model that can cope with covariances, and then we're going to do what Dick Lyons always said you should do, which is throw away the Mel-Kapstrel representation and use a better representation of speech. Yeah, you said that to me last time I visited.
Smart guy.
Okay, so the new idea is to use a better kind of module. This module already works pretty well, right? It does well at phoneme recognition. It does well at lots of other things. It can't model multiplicative interactions very well. It can model anything with enough training data, but it's not happy modeling multiplies. And multiplies are all over the place. I'll show you a bunch of places where you need multiplies. Here's the sort of main example of why you need multiplies. Suppose I want to, from a high-level description of an object, the name of the shape and its pose, its size, position, orientation. Suppose I want to generate the parts of an object. and I want them to be related correctly to each other, I could use very accurate top-down model that says, knowing the square, knowing these post parameters, I generate each piece in exactly the right position. That would require high bandwidth. Or I could be sloppy, and I could say, I'm going to generate this side, and that sort of is a representation of a distribution of where this side might be. And I'll generate corners and other sides. And they're all a bit sloppy. And if I picked one thing from each distribution, it wouldn't make a nice square. But I could also top-down specify how these things should be pieced together. In effect, I can specify a Markov random field that says what goes with what. And then I can clean this up, knowing these distributions, and pick a square like that. Of course, I might sometimes pick a square that's a slightly different orientation or a slightly different size, but it'll be a nice clean square, because I know how things go together. And so that's a much more powerful kind of generative model. And that's what we want to learn to do. And so we're going to need hidden units up here to specify interactions between visible units here, as opposed to just specifying input to visible units. There's an analogy for this, which is if I'm an officer and there's a bunch of soldiers and I want them to stand in a square, I could get out my GPS and I could say, soldier number 1, stand at these GPS coordinates, and soldier number 2, stand at these GPS coordinates. And if I use enough digits, I'll get a nice, neat rectangle. Or I could say, soldier number 1, stand roughly around here, and then soldier number 2, hold your arm out and stand this distance from soldier number 1. And that's a much better way to get a neat rectangle. It requires far less communication. So what you're doing is you're downloading roughly where people should stand, and then how they should relate to each other. But you have to specify the relations, not just where they should be. And that's what we'd like in a powerful hierarchical generative model. So we're going to aim to get units in one layer to say how units in the layer below should laterally interact when you're generating. It's going to turn out you don't need to worry about those little lateral interactions when you're recognizing, but when you're generating, you do. To do that, we're going to need things called third-order Boltzmann machines, which have three-way interactions. So Terry Sinofsky pointed out a long time ago that we have an energy function like this, where this was v and this was h, but these are just binary variables. And we could perfectly well write down an energy function like this, where three things interact, and we have a three-way weight. And if you think about these three things now, k, the state of k, is acting like a switch. When k is on, you effectively have this weight between I and j. When k is off, this weight disappears. And it happens every which way because it's symmetric. So using an energy function like this, we can allow one thing to specify how two other things should interact. So each hidden unit can specify a whole Markov random field over the pixels if we want. But that sort of begins to make you worry, because a Markov random field has a lot of parameters in it. And if you start counting indices here, if you have n of these and n of those and n of those, you get n cubed of these parameters, which is rather a lot. If you were willing to use n cubed parameters, you can now make networks that look like this. Suppose I have two images, and I want to model how images transform over time. And let's suppose I'm just moving random dots around. I have a pattern of random dots, and I translate it. Well, if I see that dot and I see that dot, that's some evidence for a particular translation. And so if I put a big positive weight there, this triangle is meant to represent that big three-way weight, then when this and this are on, they'll say it's very good to have this guy on. That'll be a nice low energy state. If I also see this pair of dots, I'll get more votes that this guy should be on, and I'll turn this guy on. If, however, this pixel went to here, I vote for this guy, and if this pixel also went to there, I vote for this guy. So these guys are going to represent coherent translations of the image, and it's going to be able to use these three-way weights to take two images and extract hidden units that represent the coherent translation. It'll also be able to take the pre-image and the translation and compute which pixels should be on here. Now what we're going to do is take that basic model and we're going to factorize it. We're going to say, I've got these three-way weights, and I've got too many of them. So I'm going to represent each three-way weight as the product of three two-way things. I'm going to introduce these factors, and each factor is going to have this many parameters, which is just per factor is just a linear number of parameters. If I have about n factors, I end up with only n squared of these weights. And if you think about how pixels transform in an image, they don't do random permutations. It's not that this pixel goes there and that one goes here. Pixels do sort of consistent things, so I don't really need n cubed parameters, because I'm just trying to model these fairly consistent transformations, of which there's a limited number, and I should be able to do it with many less parameters. And this is a way to do that. So that's going to be our new energy function, leaving out the bias terms. One way of thinking about how I'm modeling a weight is I want this tensor of three-way weights. If I take an outer product of two vectors like this, I'll get a matrix that has rank 1. If I take a three-way outer product, I'll get a tensor that has rank 1. And if I now add up a bunch of tensors like that, so each factor now, each f, specifies a rank 1 tensor, by adding up a bunch of them, I can model any tensor I like if I use n squared factors. If I use only n factors, I can model nice regular tensors, but I can't model arbitrary permutations. And that's what we want. If you ask, how does inference work now? Inference is still very simple in this model. So here's a factor. Here's the weights connecting it to, say, the pre-image. Here's the weights connecting it to the post-image. Here's the weights connecting it to the hidden units. And to do inference, what I do is this. Suppose I only had that one factor. I would multiply the pixels by these weights, add all that up, so I get a sum at this vertex. I do the same here, I get a sum at this vertex. Then I multiply these two sums together to get a message that I'm going to send to the hidden units. And as that message goes to the hidden unit, I multiply it by the weight on that connection. And so what the hidden unit will see is this weight times the product of these two sums. And that is the derivative of the energy with respect to the state of this hidden unit, which is what it needs to know to decide whether to be on or off. It wants to go into whatever state will lower the energy. And all the hidden units remain independent, even though I've got these multipliers now. So this is much better than putting in another stochastic binary unit here. If I put a stochastic binary unit in here, the hidden units would cease to be independent and inference would get tough. But this way, with a deterministic factor that's taking a product of these two sums, inference remains easy. The learning also remains easy. So this is the message that goes from factor f to hidden unit h. And that message is the product that we got at those two lower vertices, the product of the sums, that you computed on the pre-image and the post-image. And the way you learn the weight on the connection from factor f to hidden unit h is by changing the weight so as to lower the energy when you're looking at data and raise the energy when you're constructing things from the model or just reconstructing things from the hidden units you got from data. And those energy derivatives just look like this. They're just the product of the state of the hidden unit and the message that goes to it when you're looking at data, and the state of the hidden unit and the message that goes to it when you're looking at samples from the model or reconstructions. So it's still a nice pairwise learning rule. So everything is pairwise still. So you might fit it in a brain. Now, if we look at what one of these factors does when I show it random dot patterns that translate, then we can look at the weights connecting it to the pre-image. And that's a pattern of weights where white is a big positive weight, black's a big negative weight. So that would have learned a grating connecting it to the pre-image. And this will have learned a grating connecting it to the post-image. And with 100 factors, I'll show you what Roland learned. So those are the 100 factors connecting, these are the receptor fields of the factors in the pre-image. And remember, it's looking at translating dots. And these are the factors in the post-image. And you see it's basically learned the Fourier basis, and it's learned to translate things by about 90 degrees. And that's a very good way of handling translation. Mathematicians say things like, the Fourier basis is the natural basis for modeling translation. I don't really know what that means, but this learned the Fourier basis, so I'm happy. If you give it rotations, it'll learn a different basis. So this is a basis it learns for rotations. You see it learns about yin and yang here. Oops. Okay, that's the basis for rotations. One other thing you could do is train it just on single dot patterns that are translating in a coherent way, and then test it on 2 overlaid dot patterns that are translating in different directions. It's never seen that before. It's only been trained on coherent motion, but we're going to test it on what's called transparent motion. In order to see what it thinks, remember we're training it unsupervised, there's no labels anywhere. We never tell it what the motions are. We need some way of seeing what it's thinking. So we add a second hidden layer that looks at the hidden units representing transformations and is fairly sparse. So the units in that second hidden layer will be tuned to particular directions of motion. And then to see what it's thinking, we take the directions those units like, weighted by how active those units are, and that'll tell you what direction it thinks it's seeing. Now when you show it transparent motion, and you look at those units in the second hidden layer, if the two motions are within about 30 degrees, it sees a single motion at the average direction. If they're beyond about 30 degrees, it sees two different motions, and what's more, they're repelled from each other. That's exactly what happens with people, and so this is exactly how the brain works. Okay. There's going to be a lot of that kind of reasoning in this talk. I'm going to go on to time series models now. So we'd like to model not just static images, for example. We'd like to model video. To begin with, we're going to try something a bit simpler. When people do time series models, you would nearly always like to have a distributed nonlinear representation, but that's hard to learn. So people tend to do dumb things like hidden Markov models or linear dynamical systems, which either give up on the distributed or on the nonlinear, but are easy to do inference. What we're going to come up with is something that has the distributed and the nonlinear and is easy to do inference, but the learning algorithm isn't quite right, but it's good enough. It's just an approximation to maximum likelihood. And the inference also is ignoring the future and just basing things on the past. So here's a basic module, and this is with just two-way interactions. This is the restricted bolts machine with visible units and hidden units. Here are the previous visible frames. These are all going to be linear units. And so these blue connections are conditioning the current visible values on previous observed values in a linear way. So that's called an autoregressive model. The hidden units here are going to be binary hidden units. They're also conditioned on the previous visible frames. And learning is easy in this model. What you do is you take your observed data, and then given the current visible frame, and given the previous visible frames, you get input to the hidden units. They're all independent given the data, so you can separately decide what states they should be in. Once you fix states for them, you now reconstruct the current frame using the input you're getting from previous frames and using the top-down input you're getting from the hidden units. After reconstructing, you then activate the hidden units again, and you take the difference in the pairwise statistics with data here and with reconstructions here to learn these weights, and you take the difference on activities of these guys with data and with reconstructions to get a signal that you can use to learn these weights or these weights. So learning's straightforward, and it just depends on differences. And you can learn a model like this. After you've learned it, you can generate from the model by taking some previous frames. These inputs, the conditioning inputs, in effect fix the biases of these to depend on the previous frame. So they're sort of dynamic biases. And then with these biases fixed, you just go backwards and forwards for a while, and then pick a frame there, and that's your next frame you generated. Then you keep going. So we can generate from the model once it's learned, so we can see what it believes.
So you always go back 2 steps in time, or is that just an example?
Sorry?
Oh, you were just going back only 2 steps in time?
No, we're going to go back more steps in time.
Okay.
I just got lazy with the PowerPoint. Now, one direction we could go from here is to do higher level models. That is, having learned this model, where these hidden units are all independent given the data, we could say, well, what I've done is I've turned visible frames into hidden frames now. And it turns out you can get a better model if you take these hidden frames and model what's going on here, and now you put in conditioning connections between the hidden frames, and more hidden units that don't have conditioning connections, that don't interact with other hidden units, and you learn this model. And you can prove that if you do this right, then you'll get a better model of the original sequences, or you'll improve a bound on the model of the original sequences. So you can learn lots of layers like that. And when you have more layers, it generates better. But I'm going to go in a different direction. I'm going to show you how to do it with three-way connections. And we're going to apply it to motion capture data. So you put reflective markers on the joints. You have lots of infrared cameras. You figure out where the joints are in space. You know the shape of the body, so you go backwards through that to figure out the joint angles. And then a frame of data is going to consist of 50 numbers, about 50 numbers, which are joint angles and the translations and rotations of the base of the spine. Okay, so imagine we've got one of those mannequins you see in art shop windows. We get a pin stuck in the base of his spine, and we can move him around and rotate him using this pin, and he can also wiggle his legs and arms. Okay? And what we want him to do is, as we move him around, we want him to wiggle his legs and arms so his foot appears to be stationary on the ground and he appears to be walking. And he'd better wiggle his leg just right as we translate his pelvis, otherwise his foot will appear to skid on the ground. And we're going to model him. We can do a hierarchical model like I just showed you, or we can do a three-way model like this, where we condition on 6 earlier frames. Here's the current visible frame. Here's your basic Boltzmann machine, except that it's now one of these three-way things where these are factors. And we have a 1 of n style variable. So we have data and we tell it the style when we're training it. So that's sort of semi-supervised. It learns to convert that 1 of n representation into a bunch of real-valued features. And then it uses these real-valued features as one of the inputs to a factor. And what the factors are really doing is saying these real-valued features are modulating the weight matrices that you use for conditioning, and also this weight matrix that you use in your thoroughly nonlinear model. So these are modulating an autoregressive model. That's very different from switching between autoregressive models. It's much more powerful. Yeah.
I missed what this 1 of n is.
So we're going to have data of someone walking in various different styles.
Styles of walking.
A style of walking, yeah.
So in your earlier diagram where you had the history, it looked like there was nothing to keep track of the relative order of the earlier frames. They all had direct link to the current frame.
Yes.
Is there anything in the model that cares about that relative
Yeah,
order?
yeah. The weights on the connections will tell you which frame it's coming from. Right? In the earlier model, there were 2 blue lines. They're different matrices, and they have different weights on.
But there's nothing from 2 steps previous to 1 step previous, right? It skipped all the way?
It just skipped all the way, right? You
And
just,
that'll continue to happen?
yeah. In other words, there's direct connections from all 6 previous frames to the current frame
Right.
for determining the current frame.
And there weren't links from the 6th frame to the 5th earliest to the 4th?
Well, there were when you were computing what the 5th frame was, right?
Okay.
But when we're computing this frame, we have direct connections from there. Okay, so we're now going to train this model. It's relatively easy to train, especially on a GPU board. And then we're going to generate from it so we can see sort of what it learned. And we can judge if it's doing well by whether the feet slip on the ground. Oh, I need to.
Strong dinosaur and chicken.
We'll get there.
Sorry.
Here's a normal walk. Maybe. Vista willing. Okay. So that's generated from the model. He's deciding which direction to turn in. And he's deciding, he needs to make the outside leg go further than the inside leg and so on. If we have one model, but if we flip the style label to say gangly teenager, he definitely looks awkward, right? We've all been there. I think this is a computer science student. My main reason for thinking that is if you ask him to do a graceful walk, it looks like this. And that's definitely C3PO.
So
You-
it wasn't with an actor.
Now, I think this was a student, not an actor, but he's very good. You can ask him to walk softly like a cat. We're asking the model at present, right? And the model looks pretty much like the real data. The real data, obviously, the feet are planted better. But notice he can slow down and speed up again. Autoregressive models can't do things like that. Autoregressive models have a biggest eigenvalue that's either bigger than 1, in which case they explode, or it's smaller than 1, in which case they die. And the way you keep them alive is by you keep injecting random noise so they stay alive. And that's like making a horse walk by taking a dead horse and jiggling it. It's kind of, it's not good. Now, he doesn't have any model of the physics. So in order to do these kinds of stumbles, there had to be stumbles similar to that in the data. But when he stopped and which stumble he did when, he's entirely determining. We could make him do a sexy walk, but you're probably not interested in that.
Dinosaur to chicken.
You want dinosaur to chicken? Where's dinosaur to chicken?
And chicken, number 5.
Oh, no, that's dinosaur and chicken.
Oh.
That's a blend. Or maybe a switch. He's got quite a lot of footskate there, so it's probably a blend. This is doing a sexy walk, and then you flip the label to normal, and then you flip it back to sexy. It's never seen any transitions, but because it's all one model, it can do reasonable transitions.
So you have these 100 style variables. Can you decouple those from the one event style and just make up new styles by playing
Yep.
with those?
Yep. Now, you can also give it many more labels when you train it. You can give it speed, stride length, all sorts of things, and then you can control it very well. Yeah. Okay. So it can learn time series, at least for 50-dimensional data. And obviously what we want to do is apply that to video, but we haven't done that yet, except for some very simple cases. The last thing I'm going to show you is the most complicated use of these three-way models. One way of thinking of it, so that it's similar to the previous uses, is that we take an image and we make 2 copies of it, but they have to be the same. And then we insist the weights that go from a factor to this copy are the same as the weights that go from the factor to this copy. So if I equals j, WIF equals WJF. Inference is still easy. In fact, inference here will consist of you take these pixels times these weights to get a weighted sum, and then you square it, because this is going to be the same weighted sum. So inference consists of take a linear filter, square its output, and send it via these weights to the hidden units. That's exactly the model called the oriented energy model, if you use the right kind of linear filter. So it's been proposed both by vision people, by Adelson and Bergen a long time ago, in the 80s, and by neuroscientists. So neuroscientists have tried to take simple cells, I point vaguely at that, and look at what polynomial their output is of their input. And Yang Dan at Berkeley says it's between 1.7 and 2.3. And that means 2. Right. So this looks quite like models that were proposed for quite different reasons. And it just drops out of taking a 3-way energy model and factorizing it. The advantage we have is that we have a learning algorithm for all these weights now, and we have a generative model. So now we can model covariances between pixels. And the reason that's good is, well, here's one reason it's good. Suppose I ask you to define a vertical edge. Most people will say, well, a vertical edge is something that's light on this side and dark on that side. Well, no, maybe it's light on this side and dark on that side, but you know. Well, it could be light up here and dark down there, and dark up here and light down there. Okay. Or it could be a texture edge. It's getting, or it might actually be a disparity edge. Well, there might actually be motion this side and no motion that side. That's a vertical edge too. So vertical edges are a big assortment of things. And what all those statements have in common is a vertical edge is something where you shouldn't do horizontal interpolation. Generally in an image, horizontal interpolation works very well. a pixel is the average of its right and left neighbours, pretty accurately, almost all the time. Occasionally it breaks down, and the place it breaks down is where there's a vertical edge. So a real abstract definition of a vertical edge is a breakdown of horizontal interpolation. And that's what our models are going to do. A hidden unit is going to be putting in interpolation, and it's actually going to turn off, so it's sort of reverse logic. When that breaks down, it's going to turn off. So one way of seeing it is this. If this hidden unit here is on, it puts in a weight between pixel I and pixel j that's equal to this weight times this weight times this weight. Okay. Since these, okay, that's good enough. So these are controlling effectively the Markov random field between the pixels, so we can model covariances nicely. Because the hidden units are creating correlations between the visible units, reconstruction is now more difficult. We could reconstruct one image given the other image, like we did with motion. But if we want to reconstruct them both and make them identical, it gets to be harder. So we have to use a different method called hybrid Monte Carlo. Essentially, you start where the data was and let it wander away from where it was, but keeping both images the same. I'm not going to go into hybrid Monte Carlo, but it works just fine for doing the learning. And the hybrid Monte Carlo is used just to get the reconstructions. Then the learning algorithm is just the same as before. And what we're going to do is we're going to have some hidden units that are using these three-way interactions to model covariances between pixels, and other hidden units that are just modeling the means. And so we call, for mean and covariance, we call this McCarBM. Here's an example of what happens after it's learned on black and white images. Here's an image patch. Here's its reconstruction of the image patch if you don't add noise, which is very good, from the mean and covariance hidden units. Here's the stochastic reconstruction, which is also pretty good. But now we're going to do something funny. We're going to take the activations of the covariance units, the things that are modeling which pixels are the same as which other pixels, and we're going to keep those. But we're going to take the activations of the mean units, and we're going to throw those away and pretend that the means for the pixels look like this. Well, let's take this one first. We tell it all the pixels have the same value except these which are much darker. And it now tries to make that information about means fit in with this information about covariances, which is that these guys should be the same, but very different from these guys. And so it comes up with a reconstruction that looks like that, where you see it's taken this dark stuff and blurred it across this region here. If we just give it 4 dots like that, and the covariance matrix we got from there, it'll blur those dots out to make an image that looks quite like that one. So this is very like what's called the kind of watercolor model of images, where you know about where the boundaries are, and you just sort of roughly sketch in the colors of the regions, and it all looks fine to us, because we sort of slave the color boundaries to the actual where the edges are. If you reverse the colors of these, it produces the reverse image, because the covariance doesn't care at all about the signs of things. If you look at the filters it learns, the mean units, which are for sort of coloring in regions, learn these blurry filters, and by taking some combination of a few dozen of those, you can make more or less whatever colors you like anywhere. So they're very they're smooth, blurry, and multicolored, and you can make roughly the right colors. The covariance units learn something completely different. So these are what the filters learn. And you'll see that those factors, they learn high-frequency black and white edges, and then a small number of them turn into low-frequency color edges that are either red, green, or yellow, blue. And what's more, when you make it form a topographic map, using a technique I'll describe on the next slide, you get this color blob, this low-frequency color blob, in with the low-frequency black and white filters. And that's just what you see in a monkey's brain, pretty much. If you go into a monkey's brain, you see these high-frequency filters whose orientation changes smoothly as you go through the cortex tangentially, and you see these low-frequency color blobs. And most neuroscientists thought that at least must be innate. What this is saying is, no, just the structure of images and the idea of forming a topographic map is enough to get this. That doesn't mean it's not innate, it just means it doesn't need to be. So the way we get the topographic map is by there's global connectivity from the pixels to the factors. So the factors really are learning local filters. And the local filters start off colored and gradually learn to be exactly black and white. Then there's local connectivity between the factors and the hidden units. So one of these hidden units will connect to a little square of factors. And that induces a topography here. And the energy function is such that when you turn off one of these hidden units to say smoothness no longer applies, you pay a penalty. And you'd rather just pay the penalty once. And so if two factors are going to come on at the same time, it's best to connect them to the same hidden unit, so you only pay the penalty once. And so that'll cause similar factors to go to similar places in here, and we get a topographic map. For people who know about modeling images, so far as I know, nobody has yet produced a good model of patches of color images. That is a generative model that generates stuff that looks like the real data. So here's a model that was learned on 16 by 16 color images from the Berkeley database. And here's things generated from the model. And they look pretty similar. Now it's partly a trick. It's the color balance here is like the color balance there, and that makes you think they're similar. But it's partly real. I mean, most of these are smooth patches of roughly uniform color, as are most of these. There's a few more of these are smooth than those. But you also get these things where you get fairly sharp edges. So you get smoothness, then a sharp edge, then more smoothness, like you do in the real data. You even get things like corners here. We're not quite there yet, but this is the best model there is of patches of color images. And it's because it's modeling both the covariance and the means, so it's capable of saying what's the same as what, as well as what the intensities are. You can apply it for doing recognition. So this is a difficult object recognition task where there's 80 million unlabeled training images, not all of these classes, but of thousands and thousands of classes, that were collected by people at MIT. It's called the Tiny Images Database. They're 32 by 32 color images, but it's surprising what you can see in a 32 by 32 color image. And since the biggest model we're going to use has about 100 million connections, that's about 0.1 of a cubic millimeter of cortex in terms of the number of parameters. And so we have to somehow give our computer model some way of keeping up with the brain, which has a lot more hardware. And so we do it by giving a very small retina. We say, suppose the input was only 32 by 32. Maybe we can actually do something reasonable there. So as you'll see, there's a lot of variation. If you look at birds, that's a close-up of an ostrich. This is a much more typical picture of a bird. And it's hard to tell the difference between these 10 categories, particularly things like deer and horse. We deliberately chose some very similar categories, like truck and car, and deer and horse. People are pretty good at this. People won't make very many errors. That's partly because these were hand-labeled by people. But even people make some errors. We only have 50,000 training examples, 5,000 of each class, and 10,000 test examples, because we had to hand-label them. But we have a lot of unlabeled data. So we can do all this pre-training on lots of unlabeled data, and then take our covariance units and our mean units, and just try doing multinomial logistic regression on top of those, or maybe add another hidden layer and do it on top of that. So what Marc Aurelio Ranzato actually did, since he worked in Yann LeCun's lab, he actually took smaller patches, learned a model, and then strode them across the image and replicated them. So it's sort of semi-convolutional. And then took the hidden units of all of these little patches and just concatenated them to make a great big vector of 11,000 hidden units, which are both the means and the covariances. And then we're going to use that as our features and see how well we can do. And we're going to compare it with various other methods. So the sort of first comparison is just take the pixels and do logistic regression on the pixels to decide on the 10 classes. You get 36% right. If you take GIST features, which were developed by Toralba and people at MIT, which are meant to capture what's going on in an image quite well, but they're fairly low dimensional, you get 54%, so they're much better than pixels. If you take a normal RBM, which has linear units with Gaussian noise as the input variables, and then binary hidden units, and then use those binary hidden units to do classification, you get 60%. If you use one of these RBMs with both the units like these ones for doing the means, and then these units with the three-way interactions for modeling covariances, you get 69%, as long as you use a lot of these factors. And if you then learn an extra hidden layer of 8,000 units, so notice that times that's 100 million. So there's an extra 100 million connections you learn there. But that's fine, because it's unsupervised, and you just learn it on lots of data. You get up to 72%. And that's the best result so far on this database. One final thing. You can take this model that was developed for image patches, and the student who'd be doing phoneme recognition just took that code and applied it to log spectrograms, which is sort of more close to what Dick would like to see. You're not using all this Melcapsual stuff, which is designed to throw away stuff you think you don't need and get rid of lots of correlations. Instead, you're going to take data that has lots of correlations in, but we've got a model that can deal with that stuff now. And the first thing George tried on February the 20th, which was 4 layers of 1,000 hidden units on top of this, got 22.7% correct, which was the record for phone recognition on the TIMIT database, where you're not trying to do a model adapted to each speaker. And then a week later, when he'd adapted it a bit and used more frames, he was down to 21.6%. So all this stuff was designed to do vision. It wasn't designed to do phonemes. And if we treat phoneme recognition as just a vision problem on the log spectrogram, we can wipe out the speech guys, at least on small vocabulary. Another student is now at Microsoft seeing if this will work on big vocabulary as well. Yes, yeah, right. We
can give them new, better tools.
We can give them new and better tools. So here's phoneme recognition over the years. Backprop from the 80s got 26.1% correct. Over the next 20 years or so, they got that down to 24.4% using methods that weren't neurally inspired. So I'll call them artificial. We've now got down to 21.6%. An estimate of human performance is about 15%. I don't know much about how they did this estimate, I'm afraid. But we're nearly a third of the way from artificial to real. So we need 2 more ideas and we're there. OK, I'm done. I'm finished. Yeah.
Jürgen Schmidt-Schuber recently announced that he and his students have broken the world record on the MNIST dataset, so image recognition, by simply using a 7-layer feed-forward network trained with backprop, but doing it on a GPU with lots and lots of cycles.
Yes, he did indeed announce that. What he didn't announce was he's got a spectacular result. He gets down to 35 errors. What he didn't announce was there's 2 tricks involved. One trick is to use a big net with lots of layers and a GPU board. That trick by itself won't give you 35 errors. There's a second trick, which was sort of pioneered by people at Microsoft, in fact, which is to put a lot of work into producing distortions of the data so you have lots and lots of labeled data. So you take a labeled image of a 2, and you distort it in clever ways that make it still look like a 2, but be translated. So people can get down to about 40 errors.
I think I patented that already.
Good. So Dick's already patented that. So you can get down to about 40 errors by doing these distortions. What he did was even better distortions and more of them, and a much bigger net and a GPU, and got from 40 to 35, which is impressive because it's hard to make any progress there. But it won't work unless you have lots of labeled data. And what's the disguised thing is the work went into, if you look in the paper, it's all very straightforward, it's just backprop, except when you get to the section of how they generated all this extra labeled data, where there's very careful things, like if it's a 1 or a 7, they only rotate it a certain number of degrees, but if it's something else, they rotate it more degrees. I'm actually the referee for this paper, but I don't mind him knowing. I think it's very important work, but he should emphasize that they had to have labeled data to do that, and they had to put work into distortions. So for me, the lesson of that paper is, when we had small computers, you should put your effort into things like weight constraints, so you don't have too many parameters, because you've only got a small computer. As computers get bigger and faster, you can transfer your effort from, instead of tying the weights together like Jan was doing in the early days, put your effort into generating more distortions so you can inject your prior knowledge in the form of distortions, and that's much less computationally efficient, but with a big computer it's fine, and it's more flexible. So I think that's the lesson of that paper.
I didn't even need to ask a question and you answered it. Thank you.
Any other non-question?
So it seems like you've invented some kind of cortex here that has the expected property that if it does vision, it'll do sound.
Yep.
What other problems are you going to apply it to?
Maybe it'd be quicker to say the problems we're not going to apply it to.
Okay.
I can't think of any.
Stock market?
I mean, okay, let me say what the main limitation of this is for vision. We've got at least 10 billion neurons for doing vision with. Well, at least 1 billion anyway, probably 10 billion. And even though we got that many neurons and about 10 to the 13 connections for doing vision, we still have a retina that's got a very small fovea the size of my thumbnail at arm's length. And so we still take almost everything and don't look at it. And the essence of vision is not to look at almost everything intelligently. And that's why you get all these funny illusions where you don't see things. We have to do that in these models. These models are completely crazy. And all of computer vision is completely crazy, almost all of it. Because they take a uniform resolution image, and quite a big one, like 1,000 by 1,000, and they try and deal with it all at once with filters all over the image. And if they're going to do selection, they either do it by running their face detector everywhere with no intelligence, or they do sort of interest point detection at a very low level to decide what to attend to. What we do is we fixate somewhere, then on the basis of what our retina gives us, with these big pixels around the edges and small pixels in the middle, we sort of decide what we're seeing and where to look next. And by the second or third fixation, we're fixating very intelligently. And the essence of it is that vision is sampling. It's not processing everything. And that's completely missing from what I said. Now, in order to do that, you have to be able to take what you saw and where you saw it and combine them. And that's a multiply. So this module that can do multiplies is very good at combining whats and wheres to integrate information over time. That's one of the things we're working on now. But that's probably the biggest thing missing. But that is an example of having a module that's quite good, but now it's never good enough. So you have to put it together over time and use it many times. And that's what sequential reasoning and all this stuff are. So basically, as soon as people become sequential, we're not modeling that at all. We're modeling what you can do in 100 milliseconds. And so that's what's missing. But I believe that to model that sequential stuff, we need to understand what it's a sequence of. It's a sequence of these very powerful operations. And we're in a better shape now to try and model sequential AI than we were if we didn't know what a primitive operation is. If we thought a primitive operation was just deciding whether two symbols are the same, we're going to be out of luck for understanding how people do sequential stuff. Yeah.
This isn't really a fair question, but since you said you wanted to do everything with these nets, how are you going to do first order logic? Like, there exists a dog that every girl has a boy who loves.
Hang on, I'm still processing that.
Quantifiers.
right. I'm making the point that people find quantifiers quite difficult.
Oh, sure. If you can handle up to 3 quantifiers.
I would love to do that. I have not got a clue how to do it. And you will notice that in old-fashioned AI, that they used to point out to neural net people, but you can't do quantifiers, so forget it. Nowadays, when they all do graphical models, they don't actually mention that anymore because their graphical models have difficulty with it too. Some people's graphical models do. Stuart Russell and people do. Right. Yeah, some people do. But most of the graphical models of like 5 years ago don't do quantifiers either. And so a pretty good division line would be what you can do without having to deal with really sophisticated problems like that. I would love to know how we deal with that, but I don't. So yeah, I'm going to give up on that right now.
So if you had 80 million labeled images and no extra unlabeled ones, would you do your pre-training
Yes.
and then fine-tuning?
Yes.
I think that's better. But
Yeah, in Timid, that's what we have. In Timid, all the examples we have labels. It still is a big win to do the
The
pre-training.
Jürgen Schmidhuber's result I'm just hearing about seems to suggest.
Well, Jürgen Schmidhuber hasn't tried,
He hasn't
with all
tried
his
doing
distortions,
pre-training.
doing pre-training. Now, I have a student called Vinod Nair who's just produced a thesis, where he tries things like that. He tries distortions on MNIST, and he uses special distortions of his own. And the fact is, distortions help a lot, but if you do pre-training, that helps some more too. And Bengio's results, Yoshua Bengio's results, suggest that pre-training will get you to a different part of the space, even if you have all this labeled data. So clearly one thing that needs to be done is to try the pre-training and combine with all these labels. You don't have to have the pre-training, but I'll bet you it still helps. And I'll bet you it's more efficient too. It's faster. Because the pre-training is relatively fast. You don't have to learn a very good model. You get lots of rich features. And starting from there, I think you'll do better than he does just starting from random, and faster. That's just a prediction. You might even get down to 34 errors. The problem with MNIST is the error rate's so low you can't get significance. TIMID is really nice that way. They designed it well, so you get high error rates, so you can see differences.
On the time series aspect, have you seen anything that, would you get inferences or observations that are beyond the size of the time window you're using?
Sorry, I didn't understand the question.
You-
We have a limited time
you have
window.
a limited time window. After training, is there anything in the model that picks up
Nothing.
nothing?
Nothing. It cannot deal with, it can't model
It has
how...
internal state. It has internal state.
Right, but if sort of what happened 15 time steps ago really tells you what should happen now, and it only tells you what should happen now, it doesn't tell you what should happen in the intermediate 14 time steps. It just contains information across 15 time steps without having a signature at smaller time scales. You can't pick up on that. Because it's not got a hidden forward-backward algorithm. A forward-backward algorithm potentially could pick up on that, although it actually can't.
So this wouldn't pick up on things like object permanence, where
Probably
the
not.
ball rolls behind the box and comes out the other side, and you're not going to be able to. it's
Not over a long time scale, no. No. Unless you say that there's a memory involved where you go back to a previous step. It gets more complicated, right? Now, it is true that when you build the multi-level one, which you can do with the three-way connections as well as with the two-way connections, at every level you're getting a bigger time span because you get your time window, so it's going further back into the past at each level. So you get a bit like that, but that's just sort of linear.
Can you say, do you have any rules of thumb of how much unlabeled data you need to train each of the different levels and how it would change? Like, is it just linear with the number of weights, or as you go up levels, do things change?
Okay, so I have one sort of important thing to say about that, which is that if you're modeling high-dimensional data and you're trying to build an unsupervised model of the data, you need many less training examples than you would have thought if you're used to discriminative learning. When you're doing discriminative learning, there's typically very few bits per training case to constrain the parameters. The amount of constraint you get on your parameters from a training case is the number of bits it takes to specify the answer, not the number of bits it takes to specify the input. So with MNIST, you get 3.3 bits per case. If you're modeling the image, the number of bits per case is the number of bits it takes to specify the image, which is about 100 bits. So you need far fewer cases per parameter. Another way of saying it is you're modeling much richer things. And so each case is giving you much more information. So actually, we can typically model many more parameters than we have training cases. And discriminative people aren't used to that. Many less parameters than we have pixels, but many more than training cases. And in fact, he only used about 2 million cases for doing the image stuff, and it wasn't enough. It was overfitting. He should have used more. But he was fitting 100 million parameters or something. So. But basically, the only rule of thumb is many less parameters than the total number of pixels in your training data, but you can typically use many more parameters than the number of training cases. And you can't do that with normal discriminative learning. Now, if you do that, when you start discriminative training, it quickly improves things and then very quickly overfits. So you have to stop it early.
Okay. Let's thank
Thanks.
the speaker again.
Thank you.